Okay, let's unpack this. Imagine a mathematical puzzle, a real tough one, that stumped brilliant people for, what, 56 years?
56 years, yeah. A long time in any field, especially math and computing.
We're talking about the best way to multiply two grids of numbers. Matrices, specifically two 4x4 matrices.
Right, and that might sound really abstract, maybe a bit academic.
Totally. But matrix multiplication, turns out it's like the engine under the hood of almost everything computational these days.
It really is. It's the basic math driving, well, climate simulations, complex graphics in video games.
Scientific models predicting weather or particles, and yeah, the AI that's running on your phone right now are powering those huge language models everyone's talking about.
Exactly. It's bedrock linear algebra. Anytime you've got transformations, rotations, complex systems modeled as grids of numbers, you're using matrix multiplication, a lot of it.
So optimizing that's like finding a way to make the whole foundation of computing faster, more efficient.
Precisely. And efficiency in computing now, that directly means efficiency in the real world. Computation uses energy, a lot of energy.
Right. So making these basic calculations faster means you need less raw power, less compute time for the same job.
And DeepMind folks have said, optimizing this stuff, when you scale it up across huge infrastructure, it can actually reclaim significant resources.
How significant are we talking?
We're talking about freeing up compute power that's like having tens of thousands of virtual servers running nonstop globally.
Wow. Okay, so that's a real impact. Energy savings, cost savings.
It's tangible. It filters down. Even shaving off a tiny fraction of a percent on something this fundamental, multiply that by the scale of global computing, it adds up fast. It's not just, elegant math. It's practical.
So back to this 56-year-old record set by Volker Strassen back in 1969. The best way known to multiply these 4x4 complex matrices needed 49 little individual multiplications, scalar multiplications.
That's right, 49 steps. That was the benchmark for over half a century.
And it just fell, the new record, 48 multiplications.
Just one less, but yeah, a breakthrough.
And here's the kicker, the real twist. The thing that found this better way, it wasn't a human mathematician, not someone with pen and paper or even fancy math software.
Nope. It was an AI, an artificial intelligence system.
A computer program found a better way to do fundamental math than humans had in 56 years.
That's a milestone moment, isn't it?
Definitely. So today, that's what we're doing a deep dive into, that system. Google DeepMind's AlphaEvolve. But it's bigger than just one record, right? This is about the cutting edge, AI that can design and improve algorithms itself.
Exactly. AI building AI. Or maybe AI learning how to learn. It's fundamentally changing how we think about solving problems. In math, sure, but also science, engineering, everything.
It feels like a shift. AI isn't just a tool anymore.
It's moving towards being a creative partner, something that can find genuinely new solutions, things that human experts might miss or, take many more years to stumble upon.
Okay, so let's start with the basics for everyone listening. This idea, AI designing AI or discovering algorithms. What does that actually mean? How did that even work?
Well, at its core, it means we're building AI systems whose job it is to build or modify or discover other AI systems or algorithms. And they do it with pretty minimal human hand-holding once they're set up.
So it's like AI working at a higher level, a meta level.
Exactly. Instead of programming it to solve just one specific thing, you program it to find better ways to solve whole classes of problems. And that could even include the problem of designing AI itself.
Whoa. Okay.
Yeah, that ability to improve its own problem-solving methods. That's what people sometimes call meta-learning or learning to learn.
It's like instead of giving a student the answers, you teach them how to invent completely new kinds of math or new programming tricks the teacher didn't even know.
That's a great analogy. It's about finding the underlying logic, the algorithm, not just memorizing a known solution path.
And systems like AlphaEvolve, the ones doing this,
Yeah.
How are they built? What's the tech inside?
Well, they often combine the strengths of different AI approaches. Usually there are two main pillars, two key technologies working together.
Okay, what are the two pillars?
First up, you've got evolutionary algorithms.
Evolutionary algorithms. Okay, that sounds biological, like digital Darwinism, maybe?
Yeah, it's exactly the inspiration. Evolutionary algorithms, or EAs, they're search methods, ways to find good solutions that are modeled directly on natural evolution. Survival of the fittest, but for code.
How does that work?
You start with a whole population of possibilities, candidate solutions. In our case, these could be actual computer programs or maybe just representations of algorithms. Each one is like an individual in the population.
So a bunch of potential algorithms all trying to solve the same problem.
Exactly. Then you test them. You evaluate how well each one does the job. That's the fitness function. It's a score. You define maybe how fast the algorithm runs or how accurate it is or how little memory it uses. It tells you how good each one is.
Okay, and then the better ones get to reproduce, like in nature.
That's the next step. Selection. The individuals with higher fitness scores are more likely to be chosen as parents for the next generation. This creates selection pressure, pushing the whole population towards better solutions over time.
And these parents, they combine their traits somehow.
Right, through reproduction. This usually involves two main operators, crossover and mutation.
Crossover sounds like taking bits of code from two good parent programs and mixing them.
Yeah, you might swap components or code blocks or data structures between two high-performing parents to create a new offspring program.
And mutation, just random tweaks.
Pretty much. Small, random changes introduced into the offspring's code, maybe changing a parameter, swapping an instruction, altering the structure slightly. Both crossover and mutation are crucial. They explore the huge space of possible programs, generate new ideas, and stop the search getting stuck on just okay solutions.
It really does sound like you're breeding code, like in a digital terrarium or something, constantly trying new variations.
That's a perfect metaphor. And this whole cycle, evaluate fitness, select the best, reproduce with crossover mutation, create a new generation, replace the old one, it just repeats. Again and again, maybe thousands, even millions of times.
And gradually, better programs emerge.
Exactly. The population evolves towards solutions that are better and better according to your fitness criteria. This whole field goes way back, pioneers like Vogel, Rechenberg, Schwefel, John Holland. They laid the groundwork decades ago. A key technique here is genetic programming, which is specifically about evolving actual computer programs, not just parameters.
Okay, so EAs give you this powerful search method, iterative improvement based on performance. That's pillar one. What's the second?
The second pillar is large language models, LLMs.
Ah, okay. The AIs, everyone knows now. Things like Google's Gemini or OpenAI's GPT models, trained on just massive amounts of text and code.
Correct. These models, especially the modern ones built on what's called a transformer architecture, they have an incredible grasp of language, patterns, structure, syntax, semantics, all learned from those huge data sets.
That transformer architecture, that's the thing with attention, right? It helps them understand context.
Exactly. Attention mechanisms let the model weigh the importance of different parts of the input words in a sentence, or, crucially for us, tokens in a piece of code. It helps them figure out what's relevant, which is key for understanding and generating coherent, useful output.
And obviously, their ability to work with code is vital here.
Absolutely vital. Because they've seen billions of lines of code during training, they can generate new code from scratch, they can complete code snippets you start, they can understand the purpose of existing code, refactor it to make it cleaner, and even suggest pretty complex changes or optimizations based on just a high-level description or examples.
They know different programming languages, different styles.
Many of them, yeah. Though, of course, like any generative AI, you can't just trust the output blindly. It needs rigorous testing for correctness, for security, which is actually something systems like AlphaEvolve are designed to handle automatically.
We'll get to that testing part. And these LLMs are getting multimodal too, right? Not just text and code.
Yes, increasingly they can process and integrate information from different sources.
Yeah.
Text, code, images, sometimes even structured data. It adds another layer of understanding.
Okay, so you've got the evolutionary search, exploring lots of options, and you've got the LLMs, which really understand and can generate code. How do they team up? Where's the magic synergy in AlphaEvolve?
Ah, the synergy. That's the clever part. The evolutionary algorithm still provides the main framework, right? It manages the population of programs, it handles the selection based on fitness, but the LLM takes over the job of mutation and crossover.
Instead of just random changes or simple swaps.
Exactly. Instead of basic bit flips or randomly cutting and pasting code blocks, the LLM proposes intelligent changes, context-aware changes, semantically meaningful modifications.
How does it do that?
Well, you give it a parent program that's doing okay. Maybe you show it some examples of other good programs from the database. And the LLM, using its understanding of code and algorithms, suggests specific targeted edits that are way more likely to actually improve things than just a random mutation.
So it's like smart mutation, guided evolution.
Precisely. It can suggest combining ideas from different programs in sophisticated ways. It might even generate entirely new functions or algorithmic steps based on its training data. It's injecting creativity and sort of domain knowledge into the evolutionary process.
Making the search much more efficient, less random stumbling, more directed discovery.
That's the key. The LLM acts as an intelligent guide for the EA's search through the vast space of possible algorithms. It moves beyond just tweaking parameters or minor code changes towards inventing genuinely novel structures and strategies. It massively accelerates discovery.
Okay, that makes sense. So that brings us right back to AlphaEvolve. Let's walk through it. How is this system actually put together? You called it an assembly line.
Yeah, think of it like a highly automated, really sophisticated assembly line. But instead of building cars, it's building and refining computer algorithms. It's not just one big AI model. It's a whole system, an agent, made of several interconnected parts working together.
An algorithm assembly line, I like it. Okay, station one, where does it start?
It starts with the program database. This is more than just storage. It's the system's brain, its memory, its library of ideas. It holds every single program variant AlphaEvolve has ever generated, and crucially, how well each one performed when it was tested.
So a big, constantly updated catalog of attempts, successes, failures, near misses, all tagged with performance scores.
Exactly. And it's designed cleverly. It doesn't just keep the single best program. It keeps a diverse set of high-performing solutions. Techniques like MA-Elites, which stands for Multidimensional Archives of Phenotypic Elites, are an inspiration here.
MAP-Elites, what's that do?
It basically maintains a collection of elite solutions, but organized not just by how good they are overall, but by how they behave, their characteristics or phenotype. This helps maintain diversity in the population. You don't want all your programs becoming too similar, otherwise you get stuck. Diversity provides more varied genetic material for the LLMs to work with later. Concepts like island models, where you have parallel evolutionary searches that occasionally swap good ideas, also influence the database design for efficiency.
Okay, so the database holds the history and keeps things diverse. What's the next station on the line?
Next up is the prompt sampler. This component talks to the program database. Its job is to intelligently choose which programs to work on next. It picks parent programs from the database, ones that will get modified. And it also selects inspiration programs, maybe diverse ones or particularly successful ones, to give the LLM context and ideas.
So it gathers the raw materials for the next step, the code to be changed and some examples.
Exactly. And then it builds a really detailed instruction package, a prompt for the LLMs. This isn't just make this code faster, it's much richer. It can include the parent code, snippets from the inspiration code, a clear description of the problem, feedback from previous tests on this code, high-level instructions. And get this, sometimes even parts of the prompt itself can be evolved over time to make it better at guiding the LLM.
Wow, the prompts evolve too. Meta prompt evolution. Okay, so the prompt sampler builds this complex work order. Who gets it?
That goes to the LLM ensemble. This is the heart of the operation, where the new code variations are actually generated. AlphaEvolve strategically uses a mix of Google's Gemini models.
An ensemble? Why different models?
They use different models for different tasks, leveraging their specific strengths. They use Gemini Flash models quite a bit. Flash is designed for speed and efficiency, so they use it to generate a lot of potential code changes or mutants really quickly. It lets AlphaEvolve explore a wide range of possibilities fast, like casting a broad net.
Okay, so Flash is for quantity, speed, exploring lots of options.
Right, breadth. And then they bring in Gemini Pro. Pro models are more powerful, more capable. They use Pro for depth and quality. It takes the most promising ideas, maybe generated by Flash, and refines them. Or it's used to suggest bigger, more complex, maybe more innovative changes to the code structure, the kind of things that might lead to a real breakthrough.
So Flash explores, Pro refines, and makes bigger leaps. Exploitation versus exploration, almost.
That's a good way to put it. And importantly, the LLMs often generate these changes in a structured format called a diff, like how developers track code changes. It specifies exactly what lines to delete and what lines to add where.
Ah, like search, replace, that kind of thing.
Exactly like that. It's precise. It means the LLM can make targeted changes without rewriting the whole program, which is much more efficient.
Okay, LLMs propose smart changes using diffs. Where do these new program variants go next?
They head to the evaluator pool. This is maybe the most crucial step, the quality control, the testing ground. Every single new program variant generated by the LLMs gets automatically run and tested here.
Okay, the reality check station.
Definitely. And the key thing is they're tested against a user-defined fitness function. This is where the human comes back in. You tell the system what good means. Is it raw speed, low memory use, accuracy? Energy efficiency. The evaluator runs the code, maybe on some benchmark problems, and spits out objective scores based on those criteria.
So this grounds the LLM's creativity, makes sure the cool-sounding code actually works and is better according to the goals, helps avoid those LLM hallucinations?
Precisely. The AI suggests, but the objective tests verify. It has to perform. And this evaluation is heavily optimized. They might use cascades, test cheap things first, filter out obvious failures quickly to save compute. It supports multi-objective optimization, so you can ask it to find programs that balance, say, speed and memory use. Sometimes, for really tricky problems, LLMs might even provide qualitative feedback during evaluation, like why something failed, which can be fed back to the prompt sampler. And this whole pool runs tests in parallel across huge compute clusters to keep pace.
Got it. Select, prompt, generate, evaluate. What's the final step in this loop?
The evaluated program, along with its scores and maybe that feedback, gets added back into the program database. If it's good enough, it joins the elite pool. It becomes a potential parent or source of inspiration for the next round of evolution.
And that closes the loop. It fuels the next cycle.
Exactly. And the whole thing, selecting, prompting, generating, evaluating, updating the database, runs continuously. It's orchestrated by the controller, which manages this asynchronous pipeline, trying to maximize the throughput, keep everything busy, constantly exploring and refining, often running for days or even weeks until it hits a predefined compute budget or finds a solution that meets the target criteria.
It sounds incredibly autonomous once it gets going, but you said humans are still key.
Absolutely. The process is automated, but humans define the problem in the first place. And critically, the human user defines that evaluation function. They set the target, they say what success looks like, the AI optimizes towards human goals. Plus, for integrating this into real-world code bases, developers can use special markers like hashtag evolve block start and hashtag evolve block end comments in their code.
Oh, so you can tell it which part of the code to evolve.
Exactly. You can target specific functions or sections, maybe critical performance bottlenecks, within a much larger program. It can handle evolving hundreds of lines of code, potentially across different programming languages within those blocks.
Okay, so it's a powerful automated system, but guided by human goals and focus. That paints a really clear picture of how it works. So what has this thing actually done? What are the big wins, the headlines?
Right, the results. This is where you see the power of that assembly line. It's delivered some really significant breakthroughs.
Start with that matrix multiplication record we opened with.
Okay, so as we said, it found that new way to multiply two 4x4 complex matrices using just 48 scalar multiplications, down from Strassen's 49 from 1969.
Just one less step, but you said that's a big deal, like a 2% reduction?
Around 2%, yeah, which is huge for such a fundamental operation that gets called trillions upon trillions of times in big simulations and AI models.
And you mentioned this is for complex matrices, which is different from DeepMind's earlier AlphaTensor result.
Exactly. AlphaTensor found a 4x4 method using 47 multiplications, which is technically fewer, but that was in a different mathematical setting, finite fields, like binary arithmetic. Useful for some specific things like cryptography, but not as general. AlphaEvolve's 48 multiplication result is for complex numbers, which directly applies to the real numbers we use in most scientific computing, signal processing physics. It's a new state-of-the-art for a really general, widely used problem.
Did it find improvements for other matrix sizes too?
It did. They tested it on 54 different matrix multiplication tasks, and it found improvements on 14 others besides the 4x4 complex one. For instance, multiplying a 3x4 by a 4x6 matrix. The previous best was 60 multiplications. AlphaEvolve found a way using 57. That's a 4.5% speed up. It shows it's not just a one-trick pony. It can discover algorithmic improvements more broadly.
Okay, so pushing the limits in fundamental computation. What about pure math, abstract stuff? Any discoveries there?
Yeah, this was kind of surprising, actually. They pointed AlphaEvolve at over 50 open problems in mathematics. Hard problems that mathematicians have chipped away at for years, sometimes decades, across geometry, combinatorics, number theory, analysis.
Wow, and what happened?
Well, in about 3/4 of them, 75%, it managed to rediscover the best solutions already known by humans, which is impressive validation in itself, right?
Yeah, just matching the state of the art is pretty good.
But in around 20% of those problems, it found new, provably better solutions than anything previously published.
Wait, new mathematical truths discovered by an AI?
Seriously.
Yeah.
For example, in geometry, there's the kissing number problem. It asks how many identical balls you can arrange so they all touch a central ball of the same size without overlapping. In 11 dimensions, the best-known lower bound was 592. AlphaEvolve found a configuration showing that actually 593 spheres can kiss the central one.
Just one more sphere, but that's a new mathematical bound.
It's a rigorous result, yeah. Pushes the frontier in packing problems. Then in number theory, there's the Urger's minimum overlap problem, posed back in 1955. AlphaEvolve found a slightly tighter upper bound for one specific case, C5. It improved the known bound from about 0.380927 down to 0.380924.
Tiny numbers, but significant in pure math.
Exactly. And what's really cool here is that small AI found improvement. It apparently spurred more human research. Mathematicians took AlphaEvolve's specific result and built on it to improve the bound even further.
Whoa. So the AI found a foothold and humans climbed higher from there. That's collaboration.
Yeah, it really highlights the potential for these systems as research assistants, tools for human discovery. It also slightly improved bounds related to an uncertainty, inequality, and analysis. Again, a tiny numerical change, but mathematically meaningful. And in other packing problems, it found a better way to pack 11 hexagons and solve some previously unsolved cases for packing 11 and 12 hexagons. Often the way it did this was by evolving a custom search program or heuristic tailored to that specific math problem.
Okay. Pure math breakthroughs, spurring human research. That's amazing. What about the practical stuff? Optimizing things inside Google.
Right, the real-world impact. This is where you see the efficiency gains hitting critical systems.
What's the biggest example there?
Probably optimizing the Google Borg scheduler. Borg is, well, it's the gigantic system managing all the jobs and resources across Google's global data centers. Millions of machines. It's incredibly complex. AlphaEvolve discovered a simple but really effective new rule, a heuristic for how Borg should schedule certain kinds of workloads.
A new scheduling rule found by AI. What did that do?
It's been rolled out into production, and on average, it continuously reclaims about 0.7% of Google's worldwide compute resources.
0.7% doesn't sound like much.
But remember the scale. 0.7% of Google's global fleet is huge. It translates to freeing up the equivalent compute power of tens of thousands of virtual servers that were previously being underutilized or stranded due to scheduling issues.
Wow. Okay, 0.7% is massive at that scale. That's like finding free capacity hidden away.
Pretty much. And crucially, the code for this new heuristic isn't some impenetrable AI black box. It's human-readable. Engineers can understand it, debug it, trust it enough to deploy it in this mission-critical system. That trust factor is huge.
Definitely key for adoption. Okay, what else? Optimizing AI itself.
Yes, AI training optimization. They used AlphaEvolve to optimize a really low-level piece of code, a specific kernel called Pallas, that's heavily used in the infrastructure for training large models like Gemini.
Okay, hold on. AI optimizing the training code for the AI models that were probably used in AlphaEvolve. That sounds recursive.
It certainly has that flavor, doesn't it? A kernel is a small, super optimized bit of code doing a fundamental task, usually math-heavy, that gets run trillions of times during training. Optimizing them has a massive impact. AlphaEvolve found better ways to structure the matrix math inside this Pallas kernel, specifically by optimizing how it breaks down large matrices into smaller tiles for processing.
And the result? How much faster?
For that specific kernel, they got a 23% speedup. And because that kernel is used so often in training Gemini, that translated to about a 1% reduction in the total end-to-end training time for Gemini.
1% reduction on training something the size of Gemini, that must save an enormous amount of compute, energy, cost.
Absolutely substantial savings. And it also cut down the human engineering time needed for this kind of hardcore optimization from potentially weeks or months for specialists down to just days using AlphaEvolve with engineer oversight.
Faster, cheaper, and the AI helped improve the AI that helped build it. Wild. Any other big infrastructure wins? Maybe hardware?
Yeah, contributing to hardware design too. For an upcoming Google TPU, their custom AI chip, AlphaEvolve suggested rewrites to parts of the design in Verilog, the language used to actually describe chip layouts.
The AI helped design a computer chip.
It helped optimize a key arithmetic circuit, yeah. By analyzing how the circuit worked, its suggestions helped the human hardware engineers spot inefficiencies or unnecessary complexity in the blueprint, allowing them to simplify the design.
And the impact on the chip itself.
The changes, after engineers verified them, helped physically shrink the chip area slightly and reduce its power consumption, while still meeting performance targets and passing all of the verification tests. It's like AI acting as a co-designer at a really fundamental level.
That's incredible. What about compilers, the software that turns our code into machine instructions?
That too. They applied it to optimizing the low-level instructions that compilers generate for GPUs. Specifically, they looked at the XLA intermediate representation, or IR, for attention kernels, those crucial parts of transformer models like LLMs. Compilers already optimize this stuff heavily, so finding more improvements is really, really hard, even for human experts.
And AlphaEvolve found some.
It did. It found new ways to express those attention operations in the XLAIR that led to significant speedups, up to 32.5% faster for the core flash attention kernel itself, and around 15% faster for some surrounding processing steps on GPUs. It shows it can find optimizations even in areas that are already thought to be highly tuned.
Over 30% speed up on something experts and compilers have already worked hard on. Impressive.
It is. Though it's fair to add a small caveat here. While it achieved great results in many cases, there have been reports, perhaps from this or related AI-driven optimization work, that some AI-generated kernels can struggle with newer, lower precision data types, like FP16 floating point math, which is common in AI. In some specific FP16 scenarios, these AI kernels could actually be much slower than well-tuned human libraries like PyTorch, maybe only getting a fraction of the speed.
Ah, okay. So it's not a silver bullet for every single case. Performance can vary.
Right. It highlights that performance depends on the specifics, and human testing, verification, and somebody's choosing the right tool for the job are still essential. It's an evolving capability.
That makes sense. But overall, these examples, scheduling, AI training, chip design, compiler optimization, they really show AlphaEvolve isn't just theory. It's actively improving Google's core systems, and yeah, that recursive potential is definitely there.
It's finding efficiency gains at scale, automating parts of that really hard optimization work.
Okay, so DeepMind's getting these great results using AlphaEvolve on their massive infrastructure. But for this kind of powerful tech, isn't openness important? Reproducibility, getting it into the hands of more researchers.
Absolutely. That's a huge topic in AI research.
Yeah.
Reproducibility is key for scientific progress, and making powerful tools more accessible helps everyone. AlphaEvolve itself is, a proprietary Google DeepMind system, but the papers they published describing how it works and what it achieved have definitely spurred activity in the open community.
How so? Is there like an open source version people can use?
There's a project called AlphaEvolve. It's basically a community effort and an open source implementation trying to replicate the core ideas of AlphaEvolve based on what's been published.
What's the goal there? Just to see if they can do it too.
That's part of it, yeah. Independent verification is crucial. Can others reproduce the reported results using the published recipe? That builds confidence. But it's also about making the technology accessible, providing a platform other researchers or even startups can use to experiment with these AI-driven discovery techniques without needing Google-scale resources necessarily.
Have they had any success reproducing results?
There are reports, yeah. For instance, one of the results DeepMind mentioned was efficiently packing 26 circles into a square. AlphaEvolve apparently managed to get extremely close to AlphaEvolve's result, like 2.634 sum of radii versus 2.635. That kind of close match is really promising for reproducibility.
That's great. It lets the wider world play with these powerful ideas. Is AlphaEvolve the only game in town combining evolution and LLMs like this?
Oh, not at all. This combination, evolutionary algorithms plus modern AI like LLMs or deep learning, it's a super active research area right now. Lots of people are exploring different ways to blend them.
What other kinds of approaches are out there?
Well, some groups are integrating reinforcement learning, RL, into the mix. You might have systems like one called Evolutionary, where an LLM suggests solutions maybe for classic problems like bin packing or a traveling salesman, and an EA manages the population. But then an RL agent learns to give feedback not just on the solution's quality, but on the LLM strategy for generating solutions.
So the RL part helps the LLM become a better generator of ideas for the EA.
Exactly. It learns how to prompt or guide the LLM more effectively over time. It's learning how to design algorithms, another meta level up. Another big area is neural evolution, evolving neural networks themselves. Techniques like LLM-guided evolution use LLMs to suggest smart architectural changes to neural networks, like adding layers or changing connection patterns based on their training. These suggestions get tested, the best ones survive and combine.
And that leads to better AI models.
Potentially, yes. They've used it to discover improved variants of existing models, like a vision model called ExquisiteNet V2. So it's really a two-way street. EAs can help improve LLMs maybe by evolving better prompts, like with systems called EvoPrompt or Prompt Breeder, or tuning their complex settings. And LLMs can massively boost EAs by providing much smarter starting points, more intelligent mutations, or even adaptively steering the whole evolutionary search. It's a really powerful combination.
This is.
Right.
Yeah. This capability for AI to just autonomously discover and optimize algorithms, it's incredibly powerful. Huge possibilities. But that kind of power, it must raise some big questions, right? Ethical considerations, risks.
Absolutely. Whenever you develop technology that can potentially improve itself or design better versions of itself, you have to think very carefully about the implications.
You mean that idea of recursive self-improvement? The AI getting better at making itself better, potentially very quickly?
That's the long-term scenario people discuss, yes. If an AI gets good at designing algorithms, and one algorithm it designs helps it design algorithms even better, you could, theoretically, enter a cycle of accelerating capability growth. That obviously has profound implications, both positive and potentially negative, that we need to consider.
Sounds like sci-fi, but maybe less so now. What are the more immediate practical concerns today?
Well, one very concrete one is the compute cost. Right now, finding these algorithmic improvements with systems like AlphaEvolve takes a lot of computational power. Yes, the goal is to make computing more efficient later, but the discovery process itself, running these huge evolutionary loops, using powerful LLMs, evaluating millions of program variants that requires access to massive data centers, specialized hardware like TPUs, it's resource-intensive upfront.
So you spend a lot of compute now to hopefully save more compute down the line.
That's the trade-off, yeah. A big initial investment for potentially large long-term gains. And then there are the absolutely critical questions around alignment and control. As these systems get more capable, more autonomous, how do we make sure their goals stay aligned with human values? How do we ensure the optimizations they find are genuinely beneficial and don't have unintended negative consequences? How do we maintain meaningful human oversight?
Making sure the AI's definition of better is actually what we mean by better.
Exactly. I like the analogy of rocket fuel and guardrails. This AI algorithm discovery capability. It's like incredibly potent rocket fuel for science and technology. Amazing potential. But you absolutely need strong, well-designed guardrails, ethical guidelines, safety checks, robust control mechanisms to make sure that power is steered safely and towards beneficial outcomes. Capabilities racing ahead means we must race with responsibility. It's just stating the nature of powerful tech. It requires careful handling.
That makes a lot of sense. Powerful fuel needs careful steering. Okay, looking forward then. Where could this take us? If AI can design its own algorithms, what's the forecast?
Oh, the potential applications are just vast, given how versatile it seems to be already. Pretty much any field relying on computation or complex problem solving could be impacted.
What are some of the really exciting areas?
Well, accelerating scientific discovery feels huge. We talked about math, but imagine applying this to, say, drug discovery. Not just analyzing data, but AI designing entirely new drug molecules or proteins with specific therapeutic properties, predicting their effects more accurately, potentially slashing the time and costs of finding new medicines.
AI actually designing new drugs.
That's the dream many researchers are chasing, and algorithm discovery is a core part of that. Or designing quantum algorithms, finding efficient ways to program future quantum computers, which is incredibly hard for humans. Or discovering new materials with desired properties, strength, conductivity, whatever, by evolving simulated molecular structures.
Okay, science. What about software itself, where we code?
That's going to see direct impacts. Maybe truly self-optimizing compilers that learn the best way to generate code for specific chips or workloads. Automated code optimization could just become a standard step in building software. And like we saw with Gemini, AI designing more efficient AI models or training methods, that creates a feedback loop, speeding up AI development itself.
And outside the lab, beyond code, in the wider world.
Think about complex modeling, making climate simulations more accurate or faster, building better economic models, improving astrophysical simulations, and optimizing huge real-world systems, managing smart energy grids more effectively, finding better routes for global logistics, allocating resources in cloud computing even more efficiently, building on that Borg example.
It really feels like almost any system we can describe with rules or math could potentially be optimized by this approach.
If you can define the problem clearly and crucially, if you could define an objective way to measure how good a potential solution is, that fitness function, then yeah, a system like AlphaEvolve could potentially find better ways to solve it. It's automating and amplifying our ability to create the fundamental tools that run our world.
Okay, let's just pause for a second here, pause and ponder. If AI can design algorithms better than humans in some cases, breaking 56-year-old records, optimizing systems we thought were pretty good, what else could an AI-designed algorithm solve? What huge, maybe currently intractable problems might become solvable? What doors does this open? Wow. Okay, this deep dive into AlphaEvolve and this whole idea of AI designing AI, It really feels like we're seeing a fundamental shift. AI isn't just a tool executing commands anymore. It's becoming a creative partner, isn't it? Inventing things, breaking records, optimizing our world.
It really is. And it's that powerful combination, those old school ideas from evolutionary computing, but turbocharged with the pattern recognition and generation power of modern large language models that's driving this wave. It's pushing boundaries in math, science, engineering, everywhere.
It definitely makes you think about what's next as algorithms evolve.
So can we, hopefully, by using these powerful new tools wisely and responsibly.
So we want to hear from you listening. After hearing all this, what big problems do you think an AI-designed algorithm could tackle? What kind of AI that designs X would be transformative in your world, your work, something you care about?
Yeah, let us know. Send us a tweet, share your thoughts somehow, we'll collect them. And maybe we could do a follow-up mini-sode talking through some of the most interesting ideas you come up with.
Because this deep dive, really, it's just scratching the surface of a field that's moving incredibly fast.
Always more to learn, always more to discover.